This video looks at the interference, the reflection, and a special type of wave called the standing wave. So when wave hits boundaries, they reflect back, they come back. If they hit a soft or mobile boundary or loose boundary, I've heard it called a free boundary. Okay, a boundary where the string is free to move. It bounces back the same way it came in. So if I have, let's say, a wave here, I have a line here, and I have a wave approaching a boundary. If it's going to hit a loose boundary, if it's initially coming in going this way, it's going to reflect back, but it's going to reflect back the same way. Alright? Crests will be at the same spot, troughs will be at the same spot. It'll reflect back the same. Now, if it hits a hard boundary and a mobile boundary, a fixed boundary, all words for the same thing, it reflects back the opposite. So it comes back such that where this is the trough, it is now the crest. Okay, so it reflects back 180 degrees, the exact opposite. Now, standing waves are when you have two waves coming at each other and they have equal frequency. And what happens is they interfere and interact with each other in such a way that the wave appears to stand still and just vibrate up and down. Let's take a look. Alright, this will take a minute, but we have this incoming wave. So this is the red is the incident wave. That's the wave that's coming in. It's going to hit the boundary. Now that is a fixed boundary, because that's what I said I wanted it to be. That first bullet up there says fixed end. So it's going to hit the boundary and reflect back opposite. And the two waves, the incoming and the reflection wave, are going to interfere with each other. And they're going to form a combined wave. And that combined wave is the wave you actually see. Like, you wouldn't see these two individual waves. You would only see the resultant wave. So these guys wouldn't be seen. All you would see is this. And as the waves continue to combine, you get a standing wave. And you see how the wave appears not to travel? It just goes up and down, up and down. Well, this is because of the two waves interfere with each other. Now this is good fun. Here's the website if you wanted to play with it and, you know, spend some time looking at it. I think it's cool just to sit there and watch. Now the wave, a standing wave, has 2 points. They have nodes and antinodes. Nodes are the places where the wave appears to stand still, where it doesn't leave the axis or the center. Antinodes are the places where you get maximum movement. I always remember it because antinodes, A, goes with amplitude. Amplitude of antinodes. So if you go back and look at this, you see that they have A's and N's. Antinode, where it gets really big and really small, and N, where it kind of stays the same. Now here's just another look at the soft boundaries. It reflects back the same. For a hard boundary, it reflects back opposite. Now, sometimes it's a reflection back, sometimes there's just two waves on opposite sides of the string. When two waves interfere, they can pass through each other without changing. This wave is the same as this wave. They're the same wave. at one point in here, they combined, they interfered, they did some fun stuff. But it ended the exact same way it started. Same amplitude, same wavelength, same frequency. Okay? But in between, it interfered with each other. That interference deals with the law of superposition. The law of superposition says when two traveling waves encounter each other while moving, a resultant wave is found. Like that standing wave is a resultant wave of those two waves. And they're found and made by adding together the displacements of the individual waves. In other words, you take the point, at a single point, you have two wave heights, right? So one wave is this high, one wave is this high, and then you add them together. Now, if you had one that was up and one that was down, and let's say this one was up plus 3, this one was down minus 2, or actually it's not down quite that much, we're going to go with minus 1 just to make it a little bit more realistic. You'd end up with a resultant wave. What you would actually see is a wave of plus 2, because it would be plus 3 plus minus 2, which would give you plus 2. Now, when they combine to make something bigger, you get what's called constructive interference. When they combine to get something smaller, you have what is known as destructive interference. And you can get destructive interference in such a way that you have a flat line, because everything cancels out. So you get two waves, but no line. Now the last point we're going to talk about is beats. There's this thing known as the beat frequency. The beat frequency is when you have two frequencies of not the same, but similar, close frequencies. And you get like this beat pattern, which means it gets louder and quieter and louder and quieter. Okay? And the beat frequency is measured in hertz, and it equals the absolute value of the difference between the other two. And what happens is you get two waves of similar frequencies, and at certain points they combine to form a bigger wave. See right there? Those two combine to form a bigger wave than each of the individuals. While here, one is big, one's small, one's up, one's down. So they combine to form a smaller wave. Let's take a look at a beat frequency. Alright, here's an example of a beat frequency. You got two frequencies coming in. At some point they interfere and make it bigger, some smaller, and you kind of hear, loud, quiet, loud, quiet, loud, quiet. Now let's work at an example. A certain piano string is supposed to vibrate at 440 Hertz. To check its frequency, a tuning fork known to vibrate at 440 Hertz is sounded. You end up hearing a beat frequency of 4 beats per second, so 4 Hertz. What are the two possible frequencies? Now there are two possible frequencies because of this absolute value. The difference between the two frequencies must be some number, but it could be a positive or negative number. We don't know. So 4 Hertz equals the absolute value of 440 minus some other frequency. Okay, so it could be 440 minus 360. Oh, sorry, 340, not even close, minus 336. That would equal 4. Or it could be 440 minus 444, which equals negative 4. Both have an absolute value of 4. So your possible frequencies are 440 and 336. Alright, that's it for the lesson. Good luck on your homework.